so this video is going to be over how to use logarithms to take something that is nonlinear and make it linear. In regards to scatter plots anyway. So we will use power models and logarithms to find relationships between two variables, and we're going to use those to determine, or those outcomes to determine which of those is best. So transforming with logarithms. Suppose you're given a regression that is nonlinear. So any scatter plot that curves or does something that's not linear. You would like to do regression analysis with it. You basically have three options. You can graph using the natural log of the x variable if it's a logarithmic data set. So if it curves, if it is obviously logarithmic, so if it curves, starting going up and then shoots off to the right. If it is an exponential data set, then you can graph using the log of the y variable, or the natural log of the y variable, because of course if it's an equation, well, we'll get to it. And if it's a power model, so if it's any y equals x to some power, then you can take the natural log of both the x and the y, and it'll straighten it out for you. So option A, right, if it is a logarithmic function. So when we say a logarithmic function, we mean y equals log of x or y equals the natural log of x. This is something that you covered in Algebra 2. If it is a logarithmic model or a natural log, then the equation that is used to model that is y equals a plus b to the log of x, rather than y equals a times b to the x. Remember, we're trying to do a linear regression, so we want these to look as close to a linear model, a y equals a plus b to the x type model, as we possibly can, right? So the only change here would be that we have the log or the natural log of x. If we're asked to use an x to predict a y value from that equation, then it's pretty straightforward. We're just going to take our x, whatever number that is, plug it in here, and run through the calculations and end up with our y. Not too complicated. That's the easy one. If it is an exponential model, so remember, an exponential model is y equals e to the x. Now, if you remember, e to the x is the inverse of log of x, right? So if we want to undo having an exponent as our variable, then we can take the natural log of both sides, and that would get rid of it for us. So we would be left with the natural log of y equals x, or x equals natural log of y. So, and again, the idea here is to make it look as close to a y equals a plus b to the x as we can get away with, so that we can use our typical slope and intercept analysis and prediction models to analyze the data, right? So with this, what you get is you'll get an x, and the regression model will give you the log of y equaling the intercept plus the slope times the x. And if you're asked to get a value, then of course what you'll do, what you can do is say, okay, well, I'll plug in my x times my b, and then add my a, my y-intercept, so multiply by my slope and add my y-intercept. But then I have to, if I want to figure out what the y is going to be, I have to get rid of this natural log. Well, of course, in doing that, you would make both sides e to the power of this and e to the power of that. That would undo the natural log on this side, and on the right side, your equation would look like that. So basically, it's just a plug-in. If you're trying to get a value back, it would be a plug-and-chug into this equation rather than the straight-up linear model. You can always get away with saying the natural log of the predicted value would be blah, 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 but a lot of times if you're asked to pick a specific value, then it is just as simple as doing all this math and then just e to that number, right? Option C is when you have a power model. So that's any exponent, so y equals x to some power that you don't know about, right? Now, the reason that it looks different here is because we have no way of knowing what that power is going to be, right? There's no tell. It could be, different exponents on either side. the real world is a strange place and it doesn't follow easy mathematic algebraic models, so we have to manipulate them. The easiest way to do that, if neither one of these end up working, is we can just take the natural log or the logarithm of both sides. It's going to be the natural log. We use natural log. We can take the log of both sides, and that will level it out for us. So you can, using your regression equation, you'll graph the natural log of y versus the natural log of x. You'll get y equals a plus b times x, but you'll just have to remember that both my x and my y in this case have a natural log on them. And then over here, when you're asked to predict a value, well, you can do what you did before, plug in your x here, remember to take the natural log of it this time before you do all this other math to it, and then at the very end, take e to the power of that number, and that will actually be your predicted value. It's really one or two extra steps more than what it was before. It's not that much, but we'll see an example anyway. So here's an example, right? This is an example of something that is, non-linear. So we have the data on the distance from the sun the different planets are, and then how long it takes for that planet to circle the sun. So we see Mercury is very close to the sun, and it makes its trip around the sun every quarter of a year, right? So once a season. Meanwhile, Pluto, at this point, at the writing of this question, Pluto was still considered a planet. It takes 250 years, give or take, for Pluto to make one full cycle around the sun. So we'll all be dead by the time Pluto makes it around the sun once, right? Honestly, probably the same with Neptune, too. But if we look at this graph, we see this is clearly not linear. It's close. It's close to a linear model, but the further out you go, higher up it goes in a non-linear path. Now, it could be exponential. It could be a y equals e to the x type model. But it also could be a power model, like y equals x squared or x to the fourth power, or maybe, to the 3/2 power. I don't know, some exponent, right? It could be some exponential or some power on x that does it. So there are really two possibilities. It's either an exponential function or exponential model or a power model, right? We don't know. We have to test and find out. Now, I showed you in class, using your calculator, how you can take a data set and rejig it using the natural logarithms very quickly, get new data sets, and therefore get new scatter plots. So here's an example of that. This was under the assumption that it was an exponential model, so they graphed the natural log of y versus x, and then over here, they graphed the natural log of both x and y. So this is under the assumption that it is a exponential model. This is under the assumption that it is a power model. And again, we don't know what power that is necessarily. There's probably a way to do it. We don't really care, though. All right, so we know that one of the questions that we get asked about regression models and residual plots and stuff like that is, well, which one of these is the most appropriate? Well, according to this, we're trying to figure out, well, if it's appropriate, then the residual plot won't have a clear and obvious pattern. Now, we see this as something that if we did a linear regression through, we would have a very clear and obvious pattern. We'd have dots that start below, they would go above, and then they would shoot off again. We're trying to make something look linear. If we pick the right model to transform it to, then we will have a linear model. So when we compare these two, if we want to figure out which one is the correct assumption, or the most correct, I guess, we can look at which one is the closest to a straight line. And simply put, that would be option B. Therefore, we can assume that the best model to use in this case is a power model. And again, to reiterate, we don't have to know exactly what that equation would be. We don't have to know what that power is. All we have to know is that we can mimic that model very easily just by taking the natural log of our two data sets and get something that is representative. So for the Minitab output, for the computer output, we've seen this before, but we haven't really seen it with nonlinear models, but it's the same thing. You'll be given a computer output. We are told specifically that is the natural log of y versus the natural log of x, so it's really important to keep that straight. So when we're asked to give the equation for the least squares regression line, for us, we would say, okay, well, it's the natural log of the period, if you remember, it's the time it takes for it to travel around the sun. So the natural log of the period equals a plus b times the natural log of our x, our natural log of our distance from the sun. So it gives us here, remember when we're reading these, we don't care about anything over here on this side, and we don't care about the r squared adjusted. We just care about this, and then these two guys down here. This is the standard deviation of the residuals, which we don't care about right now. And this is r squared, which we also don't care about right now. But keep in mind, this is a 100%, r squared. That's really good. That's almost impossible to get normally, right? Like, we don't see that. So it looks like our y-intercept is this first value, so 0.0002544, and our natural log of, and our slope, so our number being multiplied by the natural log of distance, is 1.49986. So if we needed to come up with an equation, we would say the natural log of the period equals 0.0002544 plus 1.49986 times the natural log of the distance in astronomical units, which is how far away the Earth is from the sun, of course. Anyway, so, we have to write the equation, I guess. So let's write it down. Equation for the least square regression line. We said it is the natural log of the period equals a, which was 0.000, and there you go. That is the equation for the least square regression line. Now, back to this. So if we look at, So use your model from part B to predict the revolution for Eris, which is 9,500,000,000 miles, or 102.15 astronomical units from the sun. I'm glad they gave us the astronomical units. I didn't feel like doing them, and it wants us to show our work. All right, so first thing we got to do is just plug this into the equation. So 102.15 goes into our equation. I almost forgot to put the natural log there. That could have been bad. All right, so there's a couple ways we can do this. We can do it step by step, or we can just do it all at once, right? So we know that the predicted value is going to be after we calculate all of this stuff. So we can either calculate everything on the right and simplify it first and then get rid of the natural log, or we can get rid of the natural log now and go from there. So I'm going to show what it would look like if you're going to get rid of the natural log at the beginning and then just type it all in the calculator in one go. I like to type it in the calculator in one go because that leaves me less opportunity to make mistakes, and I am very mistake prone. So first we get the value for the period. I guess it would be the predicted period. Should include that. All right. And that will be equal to E. I'm sorry, no. So predicted period will equal E to the power of, and then all of this stuff. There you go, right? So that is what we're going to put in our equation. This side over here, E to the power of all that. So we get our calculator up. That's very large. It's the power of 0.0002. And there we go. So it looks like it'll take 1,032 years, or 1,000 and like 2 days, or like 4 days, I guess. So 1,032.02 days. So, I'm sorry. Is it days? Years. It's years. Yeah. There you go. Now the last thing that we need to talk about is whether or not the residual plot is better or worse, right? So this is the residual plot for the regression that we were using, right? So if we were talking about just in general, is this model good or bad? Is it appropriate? While we can safely say it is a better model, then we can still make the case that there is a pattern in the residual plot. So perhaps maybe it's not the most appropriate. It's still good and it's still better, but it could be even better, right? We're not accounting for some of the nuances that are going on within this. So anyway, this question specifically is saying, do we expect a prediction to be too high, too low, or just right? Now remember, our prediction was based on the x value was 102.15. So in order to figure out what that would be, we need to find the natural log of 102.15 and see if that is above the actual. So if it's, for example, between the ranges of 0 and 3, or I'm sorry, 0 and 2.5, then we would make the case that our prediction would be too high because all of the real dots are below that. If it's less than that, or if it's more than that, since all of the dots are above, then we would say, well, our prediction would be too low. So just real quick, the natural log of 102.15, I can find that out real quick. Boom. 4.62644. So it seems as if that this value is above 2.5. That would be 4.5, so that would be out here. Based on this graph, I'd say, well, this is trending back upwards again. Our line would be down here. The reality would probably be up here. So I would say our prediction is going to underestimate. Our prediction will be too low because the reality is the dots. The line is just the prediction, right? Since the dots are above, our line is below, our prediction is going to undershoot, right? We are going to be too low. And that would be our justification. Anyway, that's an example that goes through kind of the ins and outs of transforming with logarithms. You can do both the x, you can do the y, you can do both the x and the y, and then you can be asked the same questions that you would if it were a regular old linear equation. Hope this was helpful.